Yeah. Today we are going to see about control system engineering unit 2. So in general, our unit 2 is mainly dealing with about the time response analysis. So we are going to see the first and second topic. That is, we are going to see the transient steady state response, and we are going to measure the performance of first order and second order systems. Right? Okay. The first topic we are going to see about the responses. So in general, a system will have two types of responses. One is a system can able to produce a stable output, and a system can able to produce the unstable output. As for we design a system, we have to consider both the things. That is, we have to consider both. That is, your total response of a system must be equal to your transient response plus your steady state response. We have to consider both the things. What is actually a transient response? It's nothing but it has to be remains for a very short time. Your output will has to be the fluctuate. That is, it can able to produce the unstable output, right? And it is also known as the natural responses. It is also known as natural response. And in the steady state response, it is a output which is to be produced in for a very long time. That is, at for a t equal to infinity, it has to be produced. And it is also known as the forced or fixed or final responses. So this is actually important two-mark question: difference between a transient and steady state responses, right? So when we draw a graph, so this graph will be like this. The off of this graph will be the transient response, and remaining will be the steady state response. And the between, see this gap, the actual value is to be 1, but you are attaining the value of 0.98. So this is nothing but your steady state error. This has to be calculated for every system. It has to based on the initial and final value theorems. Then now, before entering into the performance measurement of first order and second order system, we are going to discuss about some type of test signals. As far as control system, we have taken four different types of test signals. Actually, the time response has the utmost response for the design and analysis of control system, because these are inherently time domain system where the time is independent variable. During the analysis of response, the variation of output with respect to the time can be studied and applying this standard test signal, and it is known as time response. To attain the satisfactory performance of the system, the output behavior of the system with respect to the time must be within the specified limit. Okay, that's why we have to consider this type of test signals. So totally I'm taking four different types of test signals. Impulse signal, otherwise it is called as a sudden shock. Why it is called as sudden shock is nothing but a very high force has to be applied within the short period of time. So see the diagram of the signals. High force has to be applied for the particular short time. That's why it is called as the impulse signal. Mostly this type of inputs we have seen in the mechanics. Step signal, the second type is a step signal. It is actually we called as a sudden change on the signal. And third signal is a ramp, and fourth is a parabolic. Parabolic, the other name is also called constant acceleration, right? And we know the graph always you have to draw versus time domain versus your input signals, right? And we have to represent the time domain. That is, we have to represent the signals in terms of time domain. So first we consider the impulse signal r of t. That value has to be the infinity at only the value of t equal to 0. Remaining everything, the value has to be 0. Then second signal, step signal, r of t will be equal to u of t. Nothing but it is a step signal, so I have to consider it as a. If it is a unit step signal, that a value must be the 1. And ramp signal, it has to be represented as t, and r of t parabolic is nothing but t square by 2. So this is a way of representing the test signals in terms of time domain. Then we have to take the Laplace domain for the particular signals. So when we have taken the Laplace transform for the impulse signal, right, it is actually a having the short width and unity area. So it is always to be the constant. The r of s value will has to be the value of 1 for impulse signal. And for coming to the step signal, it has to be treated as like we have one general formula. Take this formula. So as we are a second year student, we doesn't know about the concept in the Laplace transform. So just take this formula alone. Laplace of t power n will be equal to n factorial divided by s power n plus 1, right? So just we come to the concept here. The value is called a. So a into t power 0. So the same input signal can I write like this: a into t power 0. So a is a constant, so keep as it is. Then followed your t power 0 by using this Laplace formula. So 0 factorial divided by s power n plus 1. So totally your answer will be a by s. We know that 0 factorial will be the 1. Similarly, we have to calculate for ramp signal as well as a parabolic signal. Ramp signal, we get answer as 1 by s square, and parabolic, we have the value of 1 by s cube. Then, and one more thing, it's a main important gate question. Always they will ask the question of like integration and differentiation. What is that? Nothing but the question will be like integration of impulse signal is dash. Like that the question will be. So see the column, integration of impulse is step, integration of step is ramp, integration of ramp is parabolic, and coming to the differentiation, differentiation of step is impulse, differentiation of ramp is step, and differentiation of parabolic is ramp. So this is very, very important thing. We have to know this one. Okay, so see the diagram also. See the transform value a by s. So this is that one. If I am taking the integration, I can get the value of 1, right? So 1 is nothing but the impulse signal. This is the concept. Integration of impulse. Integration of step signal, I am getting the ramp signal. Clear? See here, it is 1 and it is 1 by s and it is 1 by s square. So keep on going. It is 1 by s cube. So keep on, we are integrating, right? So integration of impulse is step, integration of step is ramp, and it is integration of ramp is parabolic. Keep on going. Okay. Then reverse thing. So when we come back to the reverse thing, we are getting the differentiation concepts. Okay. And now we are going to discuss about the first order system, and with the help of the simple RC circuit. RC circuit is nothing but it consists of R and C, resistor and capacitor, and we know the voltage and current flowing in this one. Okay, then we have to calculate as usual EI of t, E naught of t. Input side, so it is traveling across the resistor and capacitor. You have to write, represent your resistor and capacitor in terms of I of t, then E of t. E naught of t, that is where I am taking the voltage across the capacitor alone. So that's why my answer will be 1 by c integral I of t dt. Now, as usual, we have to take the Laplace transform. Thereby, I am getting Ei of s and E naught of s. So transfer function, we know the definition. It is a Laplace transform of ratio of Laplace transform of output by input. So thereby, I am getting my final answer as 1 by 1 plus RCS. And in that, we have one small substitution, tau is equal to RC. It is nothing but a time constant. So finally, my answer will be 1 by 1 plus tau s. This is my first order main equation. Now I am having 4 different types of signals. Just now we saw. So we are going to apply now. First case, I'm taking the unit impulse signal. So definitely my value has to be 1. That is R of s value has to be 1. So I'm taking the transfer function general formula. In that R of place, I have to substitute as 1. Remaining everything has to be the same. So my final answer will be 1 by 1 plus tau s. So I am taking tau common outside in order to have the Laplace format s plus 1 by tau. So finally, I am getting my answer as e power minus t by tau. Okay, then second thing, and parallelly, when we are calculating the input test signal, parallelly you have to calculate the steady state error also, ESS. Okay, so in ESS, if you put substitute, this is the formula. It's like a final value theorem. Limit s tends to 0, s into E of s. E of s is nothing but error signal, your difference between your input and output. So you just substitute, because I am substituting R of s value has to be 1 because I am considering the case of impulse signal, thereby 1 minus 1 plus tau s. So when I am substituting s equal to 0, definitely I am getting the value of 0. Now, the second case, step signal. In that, we have to make confident that R of s equal to 1 by s. I have to substitute 1 by s. So, same substitution. In the place of R of s, I'm going to substitute 1 by s. Now, my fraction, that is my fraction will be like 1 by s into 1 plus tau s, right? So, definitely we have to go for the partial fraction. So, in that partial fraction, when I'm substituting s equal to 0, I'm getting a equal to 1, and s equal to minus 1 by tau, as by I am getting b equal to minus tau. So we know the partial fraction procedure. Afterwards, we have to substitute the value of a and b. Then I am taking tau commonly outside. Thereby, I am getting my, after taking the inverse Laplace transform, my final answer will be 1 minus e power minus t by tau. Then we have to, the next step has to calculate the steady state error. So ESS, S into E of S. E of S is nothing but output minus, that is sorry, input minus output. Then we have substitute 1 by S here because we are considering the test signal as in unit step signal, right? That's why I'm putting 1 by S. then C of S will be equal to 1 by S into 1 plus tau S. Okay, that is R of S into your general equation. Okay, now we are going to substitute S equal to 0, so thereby I am getting my answer as 0. So my both the case of impulse signal and step signal, my steady state error has to be 0 up to now. Next, third case, I'm going to apply the ramp signal. We know that R of S will be equal to 1 by S square. So 1 by S square into 1 plus 1, 1 by 1 plus tau S. As usual, we are going for the partial fraction. It is actually S square. S square has to be represented by A by S, B by S square, and C by remaining terms, right? Then substitute these three values. You have to give the values for, you have to maintain the 0 for other two values, right? We know the partial fraction procedure. So as by if you are doing like that, where I am getting my ABC values. Once I got my ABC value, you just substitute in that equation. Then we have to apply the inverse Laplace transform. Okay. So after this step, we have to apply the inverse Laplace transform. I'm getting my answer as minus tau plus t plus tau into e power minus t by tau. So in that way, I'm taking t alone as a one term has to take common. Then tau, both the two terms having the common term as tau. So I'm taking it out common. Remaining terms this will. Okay. Now the same after finding out the time response of test signal, your immediate job is to find out the steady state error. So the same formula, but here you are going to find out your R of S. R of S, it is a ramp signal, so your value will be 1 by S square, 1 by S square into 1 by tau S plus 1. The same procedure. So S is having common. And now I'm going to substitute S equal to 0. Definitely my value is to become a tau. I'm getting the value of tau. So this is the one new thing, that is both the cases of previous thing, unit step and unit impulse, your steady state error has to be 0, but now it is having the value of tau. This is the overall summary of your all the three signals. Impulse, step, ramp, its input will be 1 by S, 1 by S square we know. Then output. So final output I'm getting that one, right? So I'm writing as like for summary purpose, I'm writing all those answers at last. Then steady state, we know that two cases I'm getting 0, third case I'm getting tau. To see the answer, we already know that differentiation of step signal, we get the impulse signal, right, as per the column. The same we see the final answer, 1 minus e power minus t by tau. If I'm differentiating, I'm getting this answer. The same way, if I'm doing integration, I'm getting the bottom answer. That's the thing. If you are integrating the step signal, I'm getting ramp signal. And if I'm differentiating the step signal, I'm getting the impulse signal. Yeah. And the last case, we are going to see about the second order system. Similarly, we have to find out for all the four cases, unit, impulse, step, ramp. For all the three cases, we have to consider the performance measurement, right? So for second order system, it is like a second two stages of RC circuit. So you have to connect two more resistors and capacitors in that circuit. Therefore, and it's a general equation, transfer function will be equal to omega n square divided by s square plus 2 epsilon omega n s plus 1 omega n square. The denominator portion, right, that we call it as a characteristic equation when it is equal to 0. Okay, so when we equate the denominator equal to 0, we are getting the characteristic equation. It is one of the most important point in this place. And omega n is nothing but it is a natural undamped frequency. Its unit is radian per second. Then epsilon. Epsilon is nothing but the damping ratio. It is a very important 2-mark question. Damping ratio. It's defined as a ratio of actual damping by critical damping. So both the terms will be in terms of damping. So definitely it is a no unit. Okay. And now this based on the epsilon values, right? We have the four categories. If epsilon is equal to 0, we call it as an undamped system. And if it is a value between 0 to 1, right, it is called as a underdamped system. Then if it is epsilon values to be 1, it is called a critically damped, and epsilon is greater than 1, it is called as a overdamped system. It is another important 2-mark question based on the epsilon value, because based on the damping ratio, we classified into four categories. Okay, its value is beyond from that is from 0 to 1. Now, let us take the characteristic equation. As I already told that we have to equate the denominator portion and equal to 0. And it is like a quadratic equation. So we have to use the quadratic formula. Minus b plus or minus root of b square minus 4ac by 2a. Identify your a, b, c values. Then substitute in that value. And we are getting these two answers. That is minus epsilon omega n plus or minus. It's a very important one because we are getting two roots. See here, S1 means it is plus, and let us take like that. S2 will be the minus. We have two roots, we have to write like this. Okay. So these are the roots of second order equation. So now we are going to substitute the four different values of epsilon. As we know that epsilon equal to 0, greater than 1, and between 0 to 1, and between equal to 1. So based on the four different values, now we are going to substitute that values into the roots. Then I have to tell what type of roots we are getting. Okay. So the first case undamped. Undamped, this is my, see the first equation, it is a main equation I am taken. Now I am going to substitute epsilon equal to 0 on behalf of undamped system. If I am substituting epsilon equal to 0, my whole answer is become plus or minus j omega n, because epsilon value is to be 0. Then root of minus 1 will be there. We know that root of minus 1 value will be the j. That's why I put the j here. Remaining every term will be the 0, because I am substituting epsilon equal to 0. So see the type of the roots, it will be only consist of imaginary term. It is a purely imaginary term. When we draw it in the undamped into the S plane, right? S plane, we know that S sigma versus j omega. Sigma is a real term, minus sigma is a negative real term, j omega is imaginary term, and minus j omega is a negative imaginary term. So now we told that this undamped system will be a purely imaginary. So definitely it will be lying on the y-axis. Now coming to the second case, under damp, 0 to 1, 0 epsilon less than 1. The same equation, we are going to substitute these values, and we know that epsilon value will be within the 1, right? So now we have to rearrange the equation like this. Okay, because the value will be definitely less than or equal to 1 only, right? So I have to rearrange the equation like 1 minus epsilon square. So for that 1 minus, it's coming outside. Minus of root, we already know that it is called as a j. So your equation is little bit changed for under damped equation. Now see the my answer, it will be have some real term as well as some imaginary term. So we call that root as a complex conjugate. So sigma plus j omega. See my root's position, it will be lying on this line. Then critically damped, epsilon will be equal to 1. In that place, if I am substituting epsilon equal to 1 in the main equation, that is your top of the tabular column, right? If I am substituting epsilon equal to 1, I am getting s equal to minus omega n. That is only I am getting the real term. So its value is nothing but real and equal. And also make sure that it is a minus omega n. That's why my all answers will be lying on the negative axis of the real terms, real x-axis. Then overdamped is the last case. Epsilon will be greater than 1. And when I'm substituting, that is in that equation, if the value of epsilon will be greater than 1, right? So my answer will be like minus epsilon omega n plus or minus omega n into root of epsilon square minus 1, because it's having no problem. The epsilon value has to be greater than 1, right? So we have the equation as it is. So therefore, my type of the root will be real and unequal. So all the terms will be having only the real term, because I'm not having any j term. So that's why my axis will be my answers will be like negative real axis, because the minus will be in the first term. That's why my answers whole thing will be in the negative real axis. And one more thing, we have some substitution. Epsilon omega n is nothing but a sigma, and omega n into root of epsilon square minus 1. We call that one as a omega d. Okay, that is your damped frequencies. Some little substitution. Next, now we are going to solve the second order system with unit impulse signal. The first case I am going to discuss about the impulse signal. The next we have to discuss about the step signal. There is it is the same procedure only. Okay, so and we have to discuss the impulse signal for all the three cases. That is undamped, underdamped, overdamped, critically damped. Sorry, four cases. So we have to discuss this impulse signal with the four cases. So as usual, we have to take the main equation of second order system. In that undamped system, we know it is epsilon equal to 0. When I am substituting epsilon equal to 0 in the main equation, I am getting the answer as omega n square by s square plus omega n square, right? So this has to be split like this, omega n into omega n. Now we have some basic Laplace transform formula, inverse Laplace transform formula. If there is a numerator term will be the constant, means it will be like sine. And if it is having the s term in the numerator and the answers will be in the in this format, means the answer will be the cos at. That is nothing but inverse Laplace of s by s square plus a square, means answer is cos at. Now here look at the equation, I am getting the omega n square will be in the top. That is nothing but some constant will be in the top. So definitely the answer will be in terms of sine omega nt. This is for case 1. Now for case 2, it is critically damped. That is epsilon will be equal to 1. In that case, the same equation, if you are substituting epsilon equal to 1, look at the denominator, it will be like a plus b the whole square formula, right? So in that we have to use some two different inverse Laplace formula. Inverse Laplace of 1 by s square, we already know the formula. T power n will be equal to n factorial divided by s power n plus 1. It is a reverse thing because we are taking the inverse Laplace transform. So answer will be the 1 by s square. Then second term, we know already this formula. Inverse Laplace of 1 by s plus a will be equal to e power minus at. The same, this two logic has to be applied here because the power has to be in the denominator will be the square, so it is like 1 by s square. We have to treat like 1 by s square first, so that's why I put the t. Then s plus a, it is having some term will be in the s parameter, right? So that has to be explained like e power minus omega nt. So I hope that you are understand these two terms, t into e power minus omega nt. That is, we have to consider the 1 by s plus omega nt whole square as two different terms. That is 1 by s square and 1 by s plus a. Next, third case will be the overdamped system. Epsilon will be greater than 1. So we know that same equation. We have the same roots, right? Minus epsilon omega n plus or minus omega n into root of epsilon square minus 1. So now we are going to split these two roots. That is, I am taking s1 equal to this one and s2 equal to this one. Okay, the same two roots I am going to take. Now it is very big, right? So in order to calculate the response, we have to simplify that. The whole answer has to be take it as s1 and s2. I am proceed like that only. So normal as usual partial fraction I have to take. By substituting s equal to s1, a equal to, I am getting that value of omega n square by s1 minus s2, right? Then now I am going to substitute my s1 and s2 value here, and two terms getting cancelled, right? Then I am getting the final answer. So instead of taking s1 s2 answer directly, I'm just substitute the value or name as s1 and s2 for simple calculation. Afterwards, we are going to substitute. Okay, the same thing I'm going to substitute here s equal to s2 by, and we get my b value will be omega n square divided by s2 minus s1. Once I am take the difference between these two s2 minus s1 roots, I am getting my final answer as minus omega n by 2 into root of epsilon square minus 1. Now my A answer and B answer is ready. Now going to substitute in C of S answer. So this is my A value, this is my B value. And bottom we know that it is having S minus S1, S minus S2. Now as usual, you are going to take the inverse Laplace transform. The numerator term is a constant. So don't worry about the term, keep as it is. See here omega n by 2 into root of epsilon square minus 1. You have to keep as it is. Now we have to consider like first term as 1 by S minus S1. Second term as 1 by S minus S2. So we know that it is the inverse Laplace. We got e power s1t and e power s2t. That's all. Now afterwards we can improve that one, improve that equation. Nothing but going to substitute the s1 value and s2 value there. Okay, so both s1 and s2 have the common term as e power minus epsilon omega nt. So keep it as common. Then remaining two terms I have to put like that. Okay. Now we have one simple formula like e power theta minus e power minus theta by 2 equal to sine h theta. It is a sine hypotenuse formula. The same thing now we are going to introduce here. Consider this one has to be e power theta and this one will be the e power minus theta. 2 will be anyway it is will be in the outside. You can take that one also. So after substituting this sine h formula, your final answer will be like this. Okay. So this is for your third case, overdamped condition. Then the last case, underdamped. 0 less than epsilon less than 1. So it is value will be less than 1. Automatically your root will be like 1 minus epsilon square. Previous case and all epsilon square minus 1, but here it is 1 minus epsilon square for simple arrangement. And make sure that we have put j here. Okay, because I'm taking minus, root of minus outside, so thereby I'm getting j. Okay, then as usual I'm going to take s1 s2. What are the procedure you are following for overdamp? The same thing you are going to follow here. L by s minus s1 and b by s minus s2. Okay, now we are taking the partial fraction. I'm getting the answer as a and b value as it is. Now going to substitute in the response. This is my a value, this is my b value, right? And common term, this is that one. So I'm taking outside. My final answer will be e power s1t minus e power s2t. Now substitute the s1 and s2 value as usual. That is, what are the procedure you are following for overdamp? The same case you have to follow here. E power minus epsilon omega nt, then two terms. Okay, but here the formula is little bit different. Previously, I discussed about e power theta plus minus e power minus theta by 2 sine h theta. but here we are taking j term. Okay, so if we are using the j term, it will be some sine theta alone. It is not a hyperbolic function. So that's all. You are going to substitute that answers here and you are getting that answer. Okay. Now, overall for impulse signal, we are going to calculate the steady state error. So we know that impulse signal R of S value has to be the 1. Okay, and C of S as it is 1 into remaining thing. That is your main equation as it is come. Okay, because it is an impulse signal. That's all. We are going to substitute your S value has to be 0. Immediately all the term becomes 0. We know that steady state error for impulse signal in first order is also 0 and second order is also to be the 0. Now, summary, and write all the final answers in a one single table column for your quick revision. So undamped, I'm getting the answer as C of t will be equal to omega n sine omega n t. Critical damp, this one. And over damp. See the over damp and under damp, it will be look more or less it will be the same. But what is the difference is it is sine h and it is a sine term. Okay, it is a sine h term, it is a sine term, and it is epsilon square minus 1, it is 1 minus epsilon square. Okay, so this is the way we have to proceed for the step signal also. Okay, the step signal for the second order also you have to follow the same procedure. Okay, thank you students.